of the webinar license that we've been using for the past several months. So I'm going to stop. I'll continue to share and introduce today's speaker, who is Tom Markland. And Tom is a professor in the Department of Chemistry at Stanford University. He received his PhD working with David Monalopoulos, and then went on to a postdoctoral research with Bruce Byrne, joining the faculty at Stanford in a decade ago in 2011. He is currently an associate professor at Stanford and has received a whole list of awards, including Cottrell Scholarship, Alfred P. Sloan Fellowship, NSF Career Award. He also was the Kavli lecturer of Emerging Leader several years ago when the theme was on water. And as I mentioned, most recently, the ACS Early Career Award in Theoretical Chemistry. Today he's going to be telling us about work he's been doing in the area of aqueous chemistry, and in particular, harnessing the quantum mechanics of hydrogen bonding. And Tom, thank you for giving today's talk, and we look forward to it. And as you're bringing up your slides, I just would like to remind everyone to please post any questions you have in the chat, and we will go ahead and read the questions at the end of the talk for you. And then after the questions, we will go ahead and excuse the faculty members and provide an additional opportunity for students and postdocs to ask additional questions, either on the talk or on other aspects of careers in science, et cetera. So Tom, thank you for giving today's talk, and we're looking forward to it.
Thank you. Okay, let's do the whole this. Okay, I assume everyone can see the slides.
Perfect.
Awesome. Well, yeah, thank you very much for having me for this Phys webinar. I just wanted to start with the sort of, I don't know why that hasn't appeared. Summary of what my group overarchingly does, and of course I'm only going to be speaking about a small amount of it today. In general, of course, what my group is interested in is the interface between quantum mechanical processes and disorder. So whenever you've got something like, protons jumping about out in aqueous systems, or you've got in this case protons transferring through a imidazole, or as I'm going to talk about later today, or in this talk, protons in enzymes, or disordered interfaces in which you're trying to make electrons move, protons move around light energy. And of course, what that means is that we do a lot of stuff in both how to treat the quantum mechanics of the electrons and nuclei in the ground state, which is what I'm going to talk about today. Sorry, that should be in a box. Yeah, but also our group works a lot on things like how to include transitions between multiple electronic states. I'll work on non-adiabatic quantum dynamics, and then generally what we're interested in applying them to is the sort of processes shown here from various different parts of recent work, including this weird one with 2D electronic spectroscopy, which for some reason hasn't appeared, to try and understand spectroscopies and how they're telling us about the nature of chemical reactivity happening at disordered interfaces or heterogeneous environments. And so that's what overarchingly we're doing. Like I said, I'm mainly going to talk about this top right corner today. I'm primarily about proton transport, how to include quantum mechanics of electrons and nuclei. The methods we employ, obviously we're a theory group. To boil it down in simple stuff, what we basically employ are increasingly, although not something I'm going to talk about unless I have a couple of minutes at the end today, is techniques based on machine learning, if possible, both to predict potential energy surface and more recently to analyze experiments directly without ever having to do the atomistic simulation. Like I said, I'll talk about that briefly at the end if I have time, or if I don't have time, maybe the students can ask me to talk about that because I did bring slides on it. Or the other thing is the path integral formulation of quantum mechanics. That's something I'll talk about heavily today, and how to combine that with ab initio treatment of the electrons, in our case normally at the density functional theory level, and then combine it with path integrals to include things like zero-point energy and tunneling on that electronic surface. And the final thing, which I'll mention very briefly today, is to try and get more mileage out of these techniques, exploiting techniques in time and length scale separation. What's actually shown here is one of the approaches we often take to non-adiabatic quantum dynamics, which is the generalized quantum master equation. And again, I won't have time to talk about that in detail. Because I do have a tendency to be one of these people who goes over when they give a talk, I always do acknowledgements for my group up front, because of course they are the people who do the work. I just get to make demands and they do these great simulations and great bits of theory. And so I've highlighted in red some of the work that I'll get to today from Austin and Michael, who are currently in my group. And because this is a bit more of a historical talk, and it contains some older work, which was done by Lu Wang when she was a postdoc with me, but she's now been an assistant professor for many years at Rutgers, as well as Andre Masalek and Joe Napoli, who also have moved on to their own respective jobs. And of course, thank you for all these agencies who fund our research over the years. Okay, so one of the things I sort of wanted to stress in this was, the versatility of the hydrogen bond and why so many people in the community spend so much time examining these things. And so you can start this as a path integral simulation. We'll come back to why it looks like you don't worry, you don't need glasses. The intentionally fuzziness of these hydrogens is in one of the points of the talk today. And so obviously water is which is one of the fundamental liquids which we think of as hydrogen bonded. It obviously has all these weird properties. Is related to the fact that ice is less dense. The ice is less dense than water. It also, water can do this thing of auto-ionizing to produce protons on hydroxide, and then it can also transport via a structural mechanism its auto-ionization products. So it doesn't, and that of course leads to interesting stuff like proton transport. I thought these were videos, but apparently they're not. This is a path integral simulation we did to try and elucidate the 2D IR of protons in different acidic solutions. This is about 2 molar HCl shown there. And although I don't, for some reason, have it as a video, this is showing the green highlight of proton defects, which can be shared amongst many waters, and of course leads to this interesting structural diffusion mechanism that water has. Similarly, and again, I guess it's not a video here, that you can, Austin's work that I was mentioning has been looking at how other hydrogen bonded systems, in this case, imidazole and triazole, can conduct protons. They're of course interesting systems because they can work, those things don't boil as low as temperature as water, and so you can use them for things like high temperature proton exchange membrane fuel cell applications, and are still pretty efficient proton conductors, but they form nice chains, whereas water forms these more interesting, well, not necessarily more interesting, different three-dimensional structures. There's also interesting stuff when you start to put hydrogen bonds at the interface. There's been lots of work on how, when you either have the liquid vapor interface or oil water, basically any hydrophobic interface, that you can have interesting perturbed reactivity and selectivity at those interfaces and so that's another area of interest. And then of course, as we'll see today, enzymes can form hydrogen bond networks which can either be used for proton conduction, or in the case that we'll talk about today, it's for protons to do efficient reactivity in the active site of the enzymes. So these are the sort of things that motivate us to try and look at the hydrogen bond. The other reason that I always like to stress as to why the hydrogen bond is so versatile is this sort of matching between the strength of the hydrogen bond and the fundamental thing that controls everything under thermal conditions, which is the thermal energy KT, right? The thermal energy KT at 300 Kelvin is about half a kcal per mole. The strength of a hydrogen bond, depending on the situation you're in, is somewhere between 0.5 and 5 kcal. Obviously, if you take gas phase dimers and want to dissociate them, it's more at the upper end of that number. If you're just trying to dissociate something in a liquid where it has lots of other things it can do to stabilize when the bond is broken, you're down at the 0.5. But what it means, of course, is that the amount of energy required to break a hydrogen bond is very closely matched to the thermal energy. And so because of that, it's a interaction that can be very easily flipped from on and off in the temperature regime in which we live. Most other interactions, right, to break a covalent bond takes an incredibly large amount of energy that's much, much higher than KT in general. Whereas the hydrogen bond is really a tunable interaction in the thermal energy scale in which we naturally exist, and hence why it's such a versatile interaction. It gets used in all of these nice things to tune catalysis and things like this, because it's a very an interaction that can be very easily modulated by just simple thermal energy. And so, of course, you can today I'm going to talk a lot about including electronic and nuclear quantum effects in the hydrogen bond. But the thing I wanted to stress, of course, is that an awful lot of good work of understanding water can be done without taking that route. So, you know, if you just take water as being a fixed molecule with some positive and negative charges and then some van der Waals interactions, then, you know, you can do things like this, where you can take, this is the TIP4P 2005 water model, and you supercool and you put it below its freezing point, and you can make really, you know, this is actually an MD simulation. It's smoothed, the trajectory is smooth just to make it look less juddery, but this is truly just MD running for about a nanosecond. Of course, what you can do is you can watch this thing and, you know, hopefully, if I talked at the right speed, roughly by the time I finish speaking, of course, one will hopefully see that the ice lattice is formed, and it's really like a, you know, nice, beautiful thing. That this is not force, this is just truly heterogeneous nucleation in action under MD, classical MD conditions, based on the idea that water is just some point charges and Lerner-Jones interactions. But today I'm going to talk about when water where you really have effects that are not just due to simple electrostatic interactions. And so that's sort of going to be the focus of what I'll talk about today. And the two main effects that therefore I'm talking about are going to be 0-point energy, and less so, but also integrating is tunneling. And so, of course, 0-point energy is when you have your typical harmonic oscillator. It's the amount, this amount of energy that even at 0 Kelvin cannot be removed. And the 0-point energy is really a big contribution to the overall energy of water. So I'll start by just showing this. This is the amount of energy that a water molecule would have at 300 Kelvin, the average amount of thermal energy. So you can get that from classical equipartition. And that's the amount of energy that a water molecule would have on average classically. And now the reason I don't show the next bit until a second is, you know, you can probably guess from the fact that I have a scale that goes up to 14 here, that when I say how much does that change when you include quantum effects, it's probably going to be pretty big. And that is true. If you include the 0-point energy in a water molecule, you go from the water molecule having this amount of energy to this amount of energy, this 12 kilocalories per mole. Equivalent, you can say that the OH stretch 0-point energy is equivalent to raising the temperature of that coordinate, the amount of energy you're adding, by about 2000 Kelvin. And so it's a lot of energy that you are adding when you quantize nuclei. Another property of water that you might be interested in, of course, is the acidity of water. These are obviously measurable numbers. This is H2O, D2O, T2O, and you can see they fit on this nice line. This is quasi-harmonic scaling. It just takes the scaling relation from a harmonic oscillator, and you can see that if you assume, and this is just an assumption, but you can see the first 3 points, which are all measurable, sit on this line. What classical, i.e. the infinite mass limit, would be in terms of the pH of water, you'd be about what water would be significantly more acidic if everything. Purely classical water would be less acidic. Quantum water, which is what we actually have, because quantum effects are naturally part of the world, it makes water considerably more acidic than it would be otherwise. The one people always like is the toxicity one, which is D2O is surprisingly untoxic in the whole scheme of things, based on at least the stuff I've seen. Bacteria can live in 100% D2O. About 30% of body water is apparently the toxic amount to humans. So it's not a good way of getting rid of your enemies, because, you know, for a 70 kilogram person, you'd have to drink about 15 liters of D2O to do it. And the problem with that mainly is that D2O, last time I looked, about $1,000 per liter, so it's about a $15,000 way of harming yourself to do it. So D2O is surprisingly untoxic, but we'll see today that obviously there are quantum effects in in some enzymes where you would notice pretty different amounts if you were to do it. So these are some of the things that might motivate you. And then today I'll give you some examples of properties which really just couldn't get good qualitative ideas of what's going on unless you treat the nuclei quantum mechanically as well. And so the techniques we use to do this, which I won't dwell on because this is a phys talk, not a theory talk, and so I just want to more get to the physical insight parts of what we're doing, is what we do is a combination of what's called ab initio molecular dynamics. This is trying to solve the electronic Schrodinger equation for the electrons. We normally do it at the density functional theory level. And so what that's saying is you have these point nuclei. At each point in time, we solve for the electronic wave function or the electronic density, and then we use that to propagate the nuclei around. And that's fine. And what that will do is that is ab initio dynamics, and that gives you a classical motion, Newton's equation motion on a quantum mechanical electronic potential energy surface. But in what we want to do, we also want to be able to distinguish the difference between H2O and D2O. And for the properties we're going to look at today, which are related to free energies and things like that, you would not see a difference between H2O and D2O if you were to treat these things, nuclei classically. And so therefore, what we do on top of that is what's called path integral molecular dynamics. And what that involves simulating and annoying the zoom bar is exactly where I want to point. Let me see if I can move the zoom bar out the way. Is that rather than simulating this, which is the classical Hamiltonian p squared over 2 as the kinetic energy V of Q is the potential energy, which, like I said, we're getting by solving the electronic Schrodinger equation. Instead, in path integral, what you do is you simulate this extended system where basically the first part of this Hamiltonian just says that rather than having one world, we have P worlds where capital P is just a number. Note that's capital P to keep track. So therefore, rather than just having a red world, we have a green world, we have a blue world, we have an orange world. That's what the first part of this thing tells you to do, is just to make loads of different worlds. And that's why we colored them differently, because orange here does not see red or blue, it only sees orange. They are the first part of this Hamiltonian tells you they're completely separate worlds that go about their everyday lives differently. And the way they see each other is through this last term, which is a harmonic type term. So we put it as like a little spring, where the spring gets gets stronger as the mass or the temperature increase. And so in the classical limit, these springs are such that all these different worlds that you have collapse back down to one world. As the temperature or the mass get lower, these things can explore different things. And so the spread of these things that people will sometimes refer to as ring polymers or imaginary time paths is related to the quantum mechanical uncertainty. So as we go through, we'll see some videos where I show smeary stuff. The reason that is because in this you have multiple realizations of where the particle is. And this is a way introduced by Richard Feynman, which is a formal way for static properties to include nuclear quantum effects for distinguishable particles. We're not going to get into exchange statistics for nuclei today, it forms the basis of these methods that can be used as good approximations to quantum dynamics, methods like centroid dynamics and ring polymer dynamics. And so these things, the path integral formalism gives a nice way of including these effects in a very physically transparent way. All you're doing is you're taking a system that was previously point particles moving around an electronic surface, and now you've got these sort of ring polymer type things moving around on the surface. So it's an easy thing to implement, and it's a thing where you can take a lot of the technology that's been developed for classical simulation and apply it very easily to path integral simulation. But it also gives nice physical interpretations when if you have a one-dimensional potential and you want to go over the top of it. Of course, if you have a classical particle, at some point you have to be at the top of the barrier, whereas in the path integral formalism, what you instead have is when you're at the top of the barrier, or at least the center of the ring polymer representing the particles at the top of the barrier, it can do this thing where it sort of droops over the barrier. And so effectively what the ring polymer sees is a much flattened barrier. And so it can, this is the sort of ring polymer path integral manifestation of tunneling. You can also think this is a bit like, although this is a closed chain, it's a bit like when you have the slinky and it walks down the steps, where basically it can sort of bridge across the barrier as you go. Also, when you put this thing take this thing down to zero temperature, there's an entropic cost to all the beads going to the same place, and therefore they spread out, which gives you the manifestation of 0 point energy. You can very easily show that if you take the path integral expression and take it to the θ0 limit for, say, a harmonic oscillation, which you can do analytically, it gives you the correct 0 point energy. Of course, in these cases, we're not just having 0 point energy, it will include any higher thermal effects from higher vibrationally excited states. Sorry. Okay. So therefore, in summary, what we're doing is we're doing ab initio dynamics, quantum mechanics of the electrons, plus quantum mechanics of the nuclei, and we're combining those together, and that gives us quantum mechanical treatment of both the electrons and the nuclei in what we're doing. The one thing that I won't dwell on too much in this talk is one of the things that we've spent a lot of time working on is ways to efficiently do these simulations. As you can imagine, when you have to create lots of different worlds, it comes with a non-trivial amount of cost. The number of worlds you have to create depends on how quantum mechanical your system is. And for something like the systems we're looking at, it's typically 30 to 60 different worlds that need to be created if you just want to take the path integral formula and apply it. And that, of course, gets very expensive. We're typically looking at systems of a couple of hundred atoms, somewhere between 300 and 500 atoms. And if any, for those of you who've done an ab initio calculation, it's not cheap to do a calculation, but we also are then trying to propagate this in time. So, you know, a typical time step for a path integral simulation might be something like half a femtosecond. So to move forward in time, even classically, you need about 8 time steps if that's your time step. To do 4 femtoseconds forward in time, that's 8 ab initio calculations. But then in path integral, we also have to create all these replicas, all these different worlds, and normally to converge these things, you need on the order of at least 32. And so you can see that to evolve 4 femtoseconds in time, you end up needing about 256 ab initio calculations, which gets incredibly expensive. So what we've done over the last couple of years is develop methods that allow you to get around this. This is showing a simulation that was run for, I believe, over a nanosecond. With quantized nuclei. You can see the bobbly bits denoting all the different imaginary time paths. And the way we were able to do this is via both multiple timescale dynamics and this method we have called ring polymer contraction, which basically plays tricks in terms of noting that the imaginary time paths are very correlated with each other, and therefore, even though you need all the replicas, you can make very good approximations to what to the way they should see the electronic structure theory. And by taking advantage of that and then doing bigger time steps by using multiple timescale techniques, you can really push these things from up by a factor of about 100 or more compared to just doing a standard implementation of PIMD. So that's what's sort of taken us to the ability to rather be able to do 10 picoseconds of these things to now routinely do nanoseconds of path integral simulation. The other one, which I won't talk about too much today, is also these days is also to use machine learning to avoid having to to avoid having to actually calculate the electronic surface. Just do a couple of hundred, or maybe for certain systems like proton containing ones, a couple of thousand ab initio calculations, and train a neural network that can reproduce the electronic structure, which is something we increasingly do, but not something I'm going to talk about today. Okay, so what can one learn about water when you do this? Well, of course, you can go from classical water to correct description, i.e. that it's quantum mechanical. And one of the sort of things that one might imagine that happens when you do this is that you go from having this nice directional hydrogen bond that we think of between 2 water molecules. And what happens is that you add quantum mechanics, and as we saw in the previous video, you go to these sort of smeary hydrogen bonds where now you're less certain as where the proton is. And what that leads to is a destructuring of the liquid, a speeding up of the dynamics, right? It's a less directional hydrogen bond because now we have this uncertainty, or equivalently, if you want to think about it in energy terms, you have 0-point energy in the hydrogen bond, and so it can wiggle more in this hydrogen bond, which means it's a less directional interaction. Therefore, the net effect of this is that you're going to have a less structured liquid and a faster moving liquid. The other thing that which requires a more sophisticated potential energy surface to see is that the OH stretch here is also a relatively anharmonic particularly when it forms part of a hydrogen bond. And so whereas rigid water models, i.e. ones where the OH direction are kept fixed, or harmonic models where the thing will spread equally in the closer to the nuclei and the other direction, that you will not show, is that also down this anharmonic direction you can have the thing start to delocalize down this direction. As I stressed before, the OH interaction, the OH stretch has about 2000 Kelvin worth of 0-point energy in it, and of course that pushes you further up on the surface and allows the bond to extend. And you can see, if I was to draw this thing like this, that this you would start to say is a stronger hydrogen bond that is likely to increase the structure of the liquid and slow the dynamics. And so this is this sort of tug of war between the two competing quantum effects in the hydrogen bond network. And the interesting thing about that is it makes quantum effects and hydrogen bonds slightly less obvious to predict. If you just were like, oh, okay, every single time I do my classical simulation, I can just say, oh, well, quantum mechanics weakens it. It would be a lot easier if you could just always make the hydrogen bond slightly weaker and say that's in quantum effects. Annoyingly, depending on the regime of hydrogen bonding you're in, and we'll show some of those today, you can get either effect, which makes it hard to just parameterize it in. You can parameterize in locally, potentially, to a given description of the interactions, but it's hard to do it globally because the effect will depend on which of these two is dominated. A very clean way to see this is what's called isotope fractionation. And this is this very straightforward equilibrium. Note that there's still the same number of molecules on both sides of this equilibrium in the gas phase and the liquid phase. The difference here is all you're doing is you're taking HDO molecule, a deuterated molecule, and you're putting in the liquid in exchange for taking an H2O molecule out. So it's balanced in terms of the number of things that are in the liquid and the gas. The difference is just where the deuterium is. And the reason this is very nice is because, firstly, this free energy change, if you weren't to treat the nuclei quantum mechanically with path integral, would be to an incredibly high degree zero. The electronic energy surface has very effectively no dependence on the mass of the nuclei. It depends on the mass of the electron, and therefore this equilibrium would be zero if there was no such things as 0 point energy, etc. on the electronics, 0 point energy, etc. And so that's why this is a nice equilibrium, because it really comes about purely from the nuclear quantum effects. So what we can then do is we can, and the reason this is interesting is that this is showing this equilibrium. You can basically, if you want to turn this into a percentage, just knock off the last zero. It's of this thing, and this is experimental work from this paper. And basically, what this is showing is the separation of this equilibrium, how much HDO in the liquid versus there in the gas phase as you go through different points on the Earth. And so you can see here's North America. Europe gets like cut off on the edge, and I assume they were looking at the Pacific region more in this thing. And you can see that this is tells you that at the poles there's about 25% more deuterium in the liquid phase than there is in the atmosphere above it. And then, as you might expect, as you get nearer the equator, that separation is less. And so this is what's used in what's called isotope geothermometry, which is to try and look at the ratios of stable isotopes, and then using them to backtrack what temperatures these things are equilibrated at. You can even do this with things like oxygen 16, oxygen 18, because you can measure the ratios very accurately, and therefore, even though it's a very small thing when you're doing oxygen 16, oxygen 18, that you can get the thing. Okay, so what can we learn from simulation about this effect? So this is showing under NVT conditions. This is why this goes up all the way to the critical point, because this is not under NPT conditions, under which, of course, this would boil around here. And this is the experimental data for the amount of fractionation. So this is just proportional to this delta A, this free energy of this reaction, and where below zero corresponds to more deuterium being in the vapor, above zero corresponds to more deuterium being in the liquid. So more deuterium being in the liquid is consistent with that first quantum mechanical effect that says that the more quantum mechanical atom will be less favorable to form hydrogen bonds, and therefore will put the heavier atom in the liquid because it forms stronger hydrogen bonds. And you can see that at room temperature, that's indeed what happens. There is more deuterium in the liquid, and it prefers to throw the H2O out into the gas phase. You can simulate this. These are the simulations I was mentioning that Lou did a number of years back, and what we were able to show there by performing path integral simulations of the liquid and vapor is that you can get reasonably good reproduction. Of course, the value we can get from simulation is about here, and you can see that the value should be here, but you can see it's pretty much on the line. And then what you can do is you can use that to understand how the effects come about, and how you get this overall fractionation. So what you can do is you can project the quantum kinetic energy down different degrees of freedom. And by doing that, you can relate the changes in quantum kinetic energy rigorously to the free energy change for this reaction. And therefore, what you can do is you can break it down to the different degrees of freedom. Note, by the way, here that I'm showing a picture that looks like two water molecules, but of course, this is a liquid vapor fractionation. So this is all obtained by doing ab initio path integral simulations of the liquid and the gas phase. I'm just not showing the liquid boxes here at any point. Okay, so this first effect weakens the hydrogen bonding. And you can project down this direction and see how much this affects. If this was the only effect that you would see, then this number here, this 70, would actually be up well off the top of the graph. It would be 331. That's how much this contributes to the overall free energy change in the particular unit shown here. If you then include the other effect, of course, what we do actually is we have a simulation that includes both of them, and then project the contributions. Then what you get is that the effect of the other effect, the one that strengthens the interactions, cancels it out by minus 241. So the actual number you see in the simulation of 90 is a massive 84% cancellation between two effects. Water's normal room temperature liquid water, the overall quantum effect you see is a massive cancellation of two different quantum effects, leading to a number in this fractionation of plus 90, but it arises from a cancellation of two effects that are really pulling in the opposite directions. This also allows you to explain this. So in the experiment, you see an inversion in the experimental data. This is because these two effects have different temperature dependence. You can imagine this is sort of a waggle in the hydrogen bond, and the 0 point energy in a sort of direction like this, which is a relatively low frequency libration, is relatively small. So that quantum effect disappears very quickly with temperature. And that's the one that is trying to force this thing to be positive. This one, on the other hand, is a quantum effect due to quantization down the OH chemical bond direction. And so it's something that disappears very slowly with temperature. And that's why you see this inversion experiment. By tuning temperature, you're turning off this first effect much quicker than you're tuning off the second effect. And hence, just before water reaches its critical point, you actually obtain an inversion in the fractionation ratio, which again illustrates how close water is between the cancellation of two different quantum effects. And that's what leads me into sort of the second part of my talk, which is what happens when these effects are not in balance. Like the liquid that we live with most that is hydrogen bonded has this very large cancellation. You know, it's not far off being perfect cancellation, which is roughly happens around 500 Kelvin. What happens when you start to perturb this and have different strengths of hydrogen bonds at ambient temperature? Because that's the way you can tune the system. So this is, as I stress, rotational, this vibration, that's why they have different temperature. So that's the mini summary. Water's hydrogen bond network sits very close to perfect cancellation. And also that this is the reason that we will look into this sort of stuff, is that isotope fractionation is really important to understanding the various effects in geochemistry. So let's just think about the other types of hydrogen bond that one can have. Temperature, as we just saw, is a way of tuning the relative nuclear quantum effects in the hydrogen bond. But the other way that you can tune the balance, of course, is by creating different types of hydrogen bond. Water has one particular one that it has in the liquid, but of course, you could have things that form very weak hydrogen bonds. Typically, this is towards water has actually an OO peak around roughly about 2.8. But if you're more than that, you're in the sort of weak harmonic. The potential as you stretch the bond from the donor to the acceptor looks pretty much like a harmonic oscillator around here if you don't have a very strong acceptor. Water is roughly one of these ones that has a weakly anharmonic potential, but then you can start to get stuff where the donor and acceptor, either particularly if the acceptor is charged, or in the case that we're going to look at, the enzyme situation where the proteins fold sort of pushes everything much closer together in the active site, right? Then what you can have is you can have these things that typically have a donor acceptor distance of about 2.6, where you have what people would call low barrier hydrogen bonds. And if you really push things together, then of course you can get to something where the potential energy surface is really very flat. And so this, of course, then tunes the sorts of quantum effects that you'll see. And indeed, the most interesting quantum effects are normally found in these hydrogen bonds, because these are ones where the 0 point energy can really, as we'll see, flood particular wells with 0 point energy, at which point you'll go from having something that classically has a barrier to the proton delocalizing, but quantum mechanically will not. So the example for that is KSI. This is ketosteroidase. This is a very heavily studied enzyme. In particular, we got into it from the work of Dan Hirschlag's group and Steve Boxer's group, both at Stanford, who were looking at this. And this enzyme uses an active site hydrogen bond network to enhance this this reactions rate by, I think it's an order 10 to the 11, if I'm correct, versus doing it in solution. And so what it does is, this is the thing that the enzyme acts on. It has this active site hydrogen bond network. This thing docks in, and it has two steps. It has a proton pull, pulling off the molecule thing, and then there's a proton push back off the molecule. But in doing so, you notice that it takes the proton off at a different position, and therefore in doing so isomerizes this molecule. And you can see that the way that this thing has to be constructed is that it does have to be pretty balanced. It's pushing a proton down the network, and then it's pulling the proton back, and therefore one of the interesting things about this enzyme is often, to me, this looks like a much nastier step. You're taking off a proton here using a carboxylic acid as a base. That doesn't look like a great step that you necessarily want to do. And then you're obviously pushing it back. And but the rates of these steps have been measured, and they're generally considered to be pretty similar rates. This enzyme has done very well to balance the fact that it needs to pull of the proton and it needs to push to achieve this. And therefore, that leads to the question, which is what I'll be addressing in the remainder of this talk, which is, what's it doing in the intermediate state to have this nice balance between pushing and pulling the protons off this molecule? Okay. The thing that got us particularly interested in this is Steve Boxer and his student Stephen Fried had measured the HD pKa isotope effect. So what they did is they they put a inhibitor in here, and they made an intermediate mimic, at which point what they can do is they can look at the properties. As we'll see, what they also did was put things of different acidity in this active site here, so that you can basically study the properties of this hydrogen bond network in the intermediate state. And what they did when they did that is that they found that this tyrosine residue, if you remove this molecule, this network is so keen to pull a proton off something that if it can't pull it off this molecule, then what it does is it pulls the proton off itself at this position. This is not at the carboxylic acid, at the tyrosine residue, which formally should be much less acidic, but in practice this is a very acidic tyrosine residue. It's 6.3 versus 10 for the free amino acid, and it has a very big HD pK isotope effect. And so, of course, since one of the things we look at is isotope effects, and which arise from these nuclear quantum effects, we were sort of interested as to what happens in this case. And much like the water example that I showed before for the acidity of water, you have to be careful when you see HD. It's tempting to think that deuterium is, the classical version of hydrogen, but it's really not. Deuterium is about 2/3 as quantum mechanical as H is. And so if you again take the quasi-harmonic scaling, this is the measured experimental pKa, and you extrapolate to the classical limit, which is what you'd be doing if you just did an ab initio electrodynamic simulation with classical nuclei. This is exactly up here where you'd be simulating. And you can see that this would, this anomalously acidic residue in the KSA active site is about 6 point something, but if you extrapolate to the classical limit, it would be back to its boring old value of 10 that you see for the free amino acid in solution. So this sort of suggests that there's interesting quantum mechanics that's leading to this perturbed pKa of 6 of this residue that is instrumental in the active site hydrogen bond network that leads to this enzyme's function. So about 10,000, of course, that's a log scale, so it's about 10,000 times difference in acidity constant, pK difference of 4. So firstly, you can look at this residue, the one that's anomalously acidic, and you can just look at the crystal structure. You see here that you get distances about 2.5 and 2.55. I'll show you in a moment what we get from the simulation, but this is just taken from the experimental crystal structure. Of course, the reasons I'm talking about the distances between the oxygen is, of course, seeing the hydrogens from X-ray crystallography is basically very difficult. And therefore, what you normally can get reliably is the difference between the oxygen atoms in these things. And it's important to say, oh, well, you just said water is 2.8 electrons between the oxygens, and now it's 2.56. That doesn't sound like a big difference. The one thing to note is that's the donor acceptor distances, and hydrogen atoms don't sit on the donor or the acceptor. They sit, roughly an angstrom away. So when you go from a 2.8 to a 2.56 distance, if you're chemically bonded to this oxygen, you'd be roughly an angstrom away. If you were chemically bonded to the acceptor, you'd be about an angstrom away, which means that when you go from 2.8 angstroms to 2.56, the distance has gone from 0.8 to 0.55 distance between being chemically bonded to this side and chemically bonded to this side. So it doesn't sound like a big difference, but actually it's a pretty big difference in between the distance of the actual places the hydrogen atom would sit. So always, whenever one sees these numbers, it's always it's always sort of sensible to sort of ignore the 2 point something and just look at this number. And therefore, a 0.8 to 0.5 is a pretty big distance. A decrease in the separation of where being chemically bound to one and the other is. Also, this starts to get to the size where this is getting comparable to the thermal wavelength of the proton itself, which is on that order. Okay, so that just motivates those two things: the observation of the crystal structure and the observation of the pKa, the HD pKa shift. Of course, are experimental results that motivate that maybe it's worth looking at these things with quantum mechanical effects included. So what we want to do is we want to see where the protons bond without bias. So we do ab initio molecular dynamics treatment with the active site. All of the bits in the videos I'll show you just now are treated in the quantum mechanical region, and they're also, because we want to treat the nuclear quantum effects, they're also all quantized, although sometimes I'll only show you the full uncertainty of the protons because otherwise it just looks very fuzzy. But the entire thing in the active site of all the videos. But this is actually, just to stress, this is the sort of simulation we ran for this. So this is the overall simulation cell. So of course, outside the active site region, it's all treated atomistically, but it's treated at this sort of point charge Leonard-Jones site level. So this is QM, where inside the QM region, the bit treated electron, that we're also treating the things with path integrals. So path integral simulations for nuclear quantum effects, and so that's basically what I'm showing. But I'm going to show you what's happening in the active site to stabilize this residue. And then what we're going to do is we're going to put some different molecules in, ones which Steve Boxer and his group have done, and look at how the ionization shifts along the chain to try and understand how tuned this hydrogen bond network is. Okay, so if you do that, this is just doing a classical nuclei quantum mechanical treatment of the electrons, and then looking at how this residue is stabilized once it's been deprotonated. And you see that classically it's pretty boring. It forms two hydrogen bonds to the deprotonated residue, and not much happens. Okay. This is now if you take one of those worlds from a path integral simulation and then you watch that instead. And what you see is that now it's not boring hydrogen bonds, it's actually it's jumping back and forth effectively between being bound to one residue or the other. This, of course, includes all the zero-point energy. You can think about this as the proton jumping back and forth. Of course, in quantum mechanics, we don't normally think like that. What we would say instead is that if I show all the worlds that represent the proton isn't really jumping back and forth. It's quantum mechanically delocalized between the two adjacent residues in this deprotonated residue. And this is why there's such a big isotope effect, because as classically, it just can only stabilize by a simple hydrogen bond. Quantum mechanically, it can stabilize by quantum mechanical delocalization. You go and say, okay, well, that's a simulation. You have to put in various approximations. Can you reproduce what's in the experiment? Well, you can go and simulate the free energy change which is associated with the pKa difference. And so what I'm showing here is a delta-delta pK. Basically what this is we do a simulation of this molecule in solution, i.e. the free amino acid in solution, and look at the isotope effect here, which is pretty small. Then we look at the HD isotope effect in the active site. And so this is how much more quantum mechanical is it in the pKa. The experimental value for this is 0.57. The simulation gives 0.5. So pretty good agreement between the two, which sort of suggests that we're probably on the right track because we can predict the isotope effect that was observed experimentally in the acidity of this residue. What you can then do is ask how tuned this is for nuclear quantum effects. So you can, of course, in the simulation play games to ask this, how much the positioning affects this. As was seen, this is the distribution of OO distances between this residue and this residue. And you can see it's peaked at something very close to the crystal structure. The crystal structure gives you one number. The simulation, of course, gives you a thermal distribution of different numbers. So you can see at certain points, the aero distance gets as low as 2.3, and other places it gets as high as 2.8. But it's based around, the simulation seems to be giving a number very close to the crystal structure, which of course is not imposed on it. It was started from the crystal structure, but it could wander off if it wanted to. And so what you can then do is you can play the game of saying, okay, supposing that we did just artificially move the tyrosine 16 residue away, what would actually happen? Well, this is the energy required to take the proton from the resting position to halfway between the two residues, the perfectly shared position. And you can see that at very short aero distances, there's basically no cost to doing this. If you shove two oxygen atoms of these tyrosines together at 2.2 angstroms, then you can, then basically there's no energy cost to moving the proton to the middle. As you separate them, it becomes much more favorable to this just to be bound to this and not sitting in the middle between the two residues. And at the condition roughly that this enzyme sits at, this value here, the energy required to move the proton from being attached to tyrosine 16 to the middle is about 5 kilocalories per mole. And the reason that's relevant in this case is 5 kilocalories per mole is quite a decent, it's 10 kT to get up to here if you're just starting from the bottom of the well, which is where you start classically. If you are doing this quantum mechanically, you don't start from the bottom of the well, you start from the 0 point level, right? And the 0 point energy for this bond is about 5 kilocalories. So this is why you see in the two videos such dramatically different things. One is a hydrogen bond because you're down here. The other is you're sitting on top of the 0 point energy, so you're here, at which point basically you can just flop back and forth. So you really see the nature of the hydrogen bond in this case is really qualitatively different. In one case, it's much better described classically, it's much better described a hydrogen bond quantum mechanically. And so in this case, the enzyme's positioning of the stuff is really sort of the optimal distance for nuclear quantum effects to make the biggest difference. If you were down here at the very short distance, even classically, the proton would just flop back and forth. If you go up here, go back up here. Sorry, I was doing it on the wrong screen. Then even with the 0 point energy, you're still going to see a hydrogen bond. So in these sort of 2.5, 2.6 angstrom distances, you see really interesting effects. Let me just, in the last couple of minutes I have, show what then happens if you dock the substrate that this thing acts on into the active site. What then Steve and his group did, so this the full hydrogen bond network. We were previously just looking at this triad, but the way that the thing, this is all enzyme backbone stuff, and then this is the molecule that actually docks in. And what happens then is that you see that this forms an extended hydrogen bond network with where the proton sharing sort of shifts to this region, and this one contributes a little bit. And so what Steve and his group did is they used carbon-13 to get fractional ionization on these different residues as a function of the acidity of different phenols that they docked in. And so what they wanted to see is how tuned is this push-pull mechanism as you put something of different acidities in here. And what you find is that when you put in a phenol which matches the actual substrate this thing acts on in the active site, then this is where you see very large amount of proton sharing between 16, 57 that we were concentrating on before. So these protons are incredibly heavily shared when you put something in that matches the pK of the thing that actually acts on. And so this is a test on how tuned is the hydrogen bond network. So what we can then do is we can do a simulation of that, and what you see is indeed, looking at the video, you can see that this is the these are the backbone. This is the molecule that is part of the enzyme that gets reacted on by the enzyme, and you can see these are these look very localized. You can also quantify that. And this is just showing if you just draw them as individual realizations. This is still quantum mechanical treatment of the nuclei. It's just showing how often they jump back and forth. But then, of course, you can change that into the fractional ionization that Steve gets from his carbon-13 measurements, and this is what we get. We get these points here for the fractional ionization. So with the same phenol derivative here. So we definitely agree with him that this is this pKa of the molecule here. You have incredibly heavy sharing between these three residues. There is not really saying that one has ownership like they are in this pK range or this pK range. There's really they are distributing the protons throughout this enzyme network. So that brings me to the the final summary for this part, which is that the nuclear quantum effects allow you to explain this very large amount of proton sharing. And really, this is something that you really need the quantum mechanics of both the electrons and the nuclei to do, because it's coming from 0 point energy combined with the fact that you can actually, that the electronic structure allows a change in the chemical bonding. So that's that. And so hopefully in this talk, and as I said, there's many things I was trying to work out what the reason I gave my talk title so last minute, which I know it was because I was, so many things I was excited to talk about. And so, but I hopefully today I've given you an indication of why nuclear quantum effects can be important, and that it's now practical to do them with ab initio surfaces and all this sort of stuff. And I think I will probably stop there, because I was going to talk briefly about our recent work with machine learning to analyze NMR, but I think I've already gone over, so I will stop there. And if somebody wants to ask me about that, then I will I will do that. But if not, I'll talk about it at ACS. So,
Thanks, Tom. Virtual, real applause, etc. Again, I will remind people that please post your questions in the chat, and I'm going to let Rodrigo and Carlos ask the questions as they come in.
Okay, I'll go ahead and get discussion started. This is a question from Alexander Eisner, and his question is, does proximity of simple ions influence the anharmonicity of the OH bond? Yes, so if you have a particularly charged dense ion, then yes, you're going to get a lot more anharmonic bond to it. So I mean, it obviously if it's a very charged diffuse ion like iodine or something, you're not going to get too much. But if it's something that's small charged dense ion, negative ion, then normally you're going to get decent proton sharing. Or similarly, of course, if you're dealing with acids, which are very, where they're also very positive, where they're holding a lot of positive charge themselves, and you've got like chloride as the counter ion, you will see sharing between them. So we've done with Mike Fayer stuff right up to the solubility limit of HCl, which was to use an IR probe he had to look at the on-off rate of proton hopping. And yeah, in those ones, you also start to see, obviously, that you start to actually see intact HCl pairs, but that's at like 10 molar. The stuff I was showing earlier is like 2 molar. Yes, the answer is definitely anything that is a very good acceptor of the hydrogen bond is going to give you a much more anharmonic potential. Thank you.
Okay, so I'll ask the next question. Very nice talk, by the way. This is Carlos here. My question is you've shown that the quantum effects make a pretty big difference, when it comes to pKa and so on. So my question is it possible to apply a phenomenological correction, so to speak, to a classical model that will take into account some of these quantum effects, or is there no hope? Is always, ring polymer necessary to calculate all these effects?
I think there are certainly cases where you can do it. I mean, I think the success of classical force fields sort of reflects the fact that if you are prepared to parameterize effectively a free energy surface rather than a potential energy surface, you can get quite a lot of mileage with that. So definitely the fact that you can get water potentials that when you run them classically give pretty good properties is effectively what you're really doing is you're parameterizing in an effective quantum effect on top of the free energy surface. And that's something that is obviously really difficult to do with ab initio, because the whole point of ab initio is it should be the raw potential energy surface that the electrons are dictating. With potential, with stuff, in principle, yes. I mean, and it's been done, like you could basically view that what you're doing is that you have a particular point on the path and it sees an effective potential from the rest of the stuff that you could integrate out. And in that doing at a particular state point, you could do a very faithful reproduction of the nuclear quantum effects at that particular state point. It's like more a problem with ab initio though, because you're obviously not trying to parameterize that. You're trying to hope that it's as close as possible to the real ground state potential energy surface.
Thank you. That was very interesting.
Okay, our next question comes from Anne McCoy. And the question is, can you comment on how the heavy atom motions tune the H bond strength and how this impacts the HOD-HOH exchange?
Sorry, can you say that again? Because I got distracted by what questions were in the chat at that. I'm sorry.
Sure. The question is whether you can comment on how the heavy atom motions tune the H bond strength and how this impacts the HOD-HOH exchange.
Yeah, they're definitely very intertwined because, as the picture was showing with the OO distance, where we were just like artificially moving the OO distance, as the OO distance moves, it changes the potential energy surface for the proton to hop massively. And in doing so, but it's also a circular effect in the sense that whenever there's a strong hydrogen bond, it makes the OO distances. So they're very, very strongly correlated. And even I don't think I've got it in backup slides today, but yeah, we've looked very heavily at this, and there is very, very strong correlation between the heavy atom motion and the ability to do this. Was that answering Anne's question, or am I answering something slightly different? Okay, good. But yeah, it's really important how the heavy atoms are allowed to fluctuate.
Great. The next question comes from another audience member, Justin Pinka. Says, regarding the path integral MD, are pairwise interaction calculations between an ion and hydrogen done for every individual hydrogen, or some mean between the ring of the hydrogens?
So the way the path integral actually works is that if you let's just go back to where I had it, is the reason I like to describe this thing as different worlds is not to try and sound fancy and exotic. It's because it's the best way of actually thinking about what the simulation is really doing. The important, sometimes people say to me, oh, you're used to simulating ring polymers. I'm like, yeah, but they're not the ring polymers that if you were to chemically create, you would have, right? If this was truly a polymer made of 4 different elements, then of course, red would see blue and blue would see green and everything. The reason I like to talk about the different worlds and then putting springs between them is, let's say, in answer to the person's question, this was a hydrogen and this was a chloride ion. The way that it would see it is that they would both have ring polymers representing them, and this realization of the hydrogen would see this realization would see this, and the only way they know about each other is they have springs on the same atom as each other. They do not see each other through like red to blue here. That firstly means it's computationally cheaper than it would be otherwise, because you have potentially because you have a lot of weird interactions that you'd otherwise have to calculate if you were doing a pairwise force field. You don't have to do that. There is no pairwise interaction between this and that. You can, in principle, by the way, take this if you thought this was heavy enough. You could take the classical limit, at which point this could be represented by 1 point, at which point you'd still have a red to that point, blue to that point, orange to that same point interaction. People do that. I wouldn't normally advise it because it doesn't normally save you really any computer time. And actually, relating to Anne's question, whenever you have even something that's a heavy atom that's involved in a quantum mechanical process, treating them on uneven footings can be really dangerous, because you've given the H a load of 0-point energy and you're not giving the oxygen its corresponding part of the covalent bond. And then you get into really dicey things, because you're basically having the quantum guy fight with the classical guy when they're not on even footing. So, but yeah, I hope I maybe over answered the question, but yes, the answer is that if you have something interacting with iron, you have to be careful to note that the reason I color these different worlds is because there isn't the cross interaction. They only see each individual replica.
Thank you.
Our next question from the audience comes from Miles Edwards. And the question is, are there any heuristics of quantum nuclear effects of water that can be summarized from this work?
I don't quite know what, I mean, I would say the main thing I would take away from water is that you have to be very careful about the fact that there are 2 quantum effects and they happen to cancel. But if you start messing with things and putting like ions in, or you put an excess proton in, then that balance all falls apart. And so, for example, once you put protons in water, you basically that makes the chemical bond to the proton defect, or the hydrogen bond to proton defect, are much more anharmonic than they are to water, and therefore everything falls apart in terms of this cancellation. You go much more to the thing where the strengthening effect starts to play a role. And so the main heuristic I would take away, I guess, is just that is that you have to be careful with these things. You can sometimes get away with stuff, but definitely really think about both the fact that quantum effects don't just universally weaken every interaction. They can strengthen chemical interactions, and and yeah, just be thinking of the two mechanisms and which one you're favoring, because I always find it a very easy way when somebody says, oh, I've seen a weird isotope effect. Normally you can start to break it down as to which one of these is dominating. So there's some really nice work by Angelos Michaelides and Mariana Rossi on like DNA base pairs. And that was one of these things where they saw a weird quantum effect and they were like, oh, maybe there'll be a bigger quantum effect if we lower the temperature. And the quantum effect got smaller because it was, because again, and you know, we normally expect quantum effects to get bigger, but of course, when these things cancel, it means that they can actually have the opposite effect as a function of temperature, because as I was showing in that example, you're tuning two relative effects. And if you're, and therefore you can't guarantee that, that they will necessarily, that, you know, that lowering temperature will make the quantum effect bigger. And those DNA-based pair examples where they look at the free energy, you decrease the temperature and the quantum effect on their binding goes down rather than up. So smaller quantum effects at lower temperatures. So yeah, there's a lot of counterintuitive stuff that you can get out of this.
Thank you. Okay, and then the last question from the audience before we go into the session with just the students and postdocs is from Michael Green. Michael asked, can you see charge transfer to a neighboring ion such as potassium when it's near a hydrogen bond? And does this affect the hydrogen bond strength?
So charge transfer is a really interesting one. We actually have I don't think we did it with potassium ions, but we did it with a load of different pairs, and we actually looked at the electronic charge transfer as a function of the different strengths of hydrogen bonds. It's a chemical physics letter with Christoph Schramm from a couple of maybe 6-7 years ago, and we looked at the amount of charge transfer, and that's one of these things that really does modulate a lot. Lou in her independent group has done some really nice work looking at like the NMR chemical shifts. And of course, as we know, NMR chemical shifts are very related to shielding the amount of electron density, a very good probe on that. And the answer is yes, NMR chemical shifts are one of these things that shift markedly when you add nuclear quantum effects for lots of different systems. And so I think that would be the closest, particularly for potassium ion. I'm not sure, I'm trying to remember what we did in that paper. I think we did sodium and lithium. I don't think offhand we did potassium. I could be wrong, but broadly speaking, yeah, if you're interested in where the electron density is, that's one of the things that's going to be very sensitive to nuclear quantum effects. And yeah, like I said, I would advise, I couldn't remember what the name of the paper was, but yeah, that you said, but yeah, I would advise maybe looking at that CLPL paper, because we did look at like both the shift in the charge distribution and the breadth in the charge distribution, and it does change markedly.
Thank you.
And I think at this stage, I want to thank again everyone for coming and ask the people who are not students or postdocs to please sign off, and students